hyperconjugation. You will see hyperconjugation in ethyl carbocation. The shape of ethyl carbocation is somewhat like this. One carbon atom is attached with 3 hydrogen atoms and one adjacent carbon atom and is sp3 hybridized having tetrahedral orientation. The other carbon atom is positively charged attached with 2 hydrogens and one adjacent carbon atom. According to the VS-EPR theory, this carbon atom is bound to have sp2 hybridization having planar orientation. Now what we have not shown here is empty p orbital of carbon containing positive charge. Now this p orbital is perpendicular to the plane of CH bond of carbon containing positive charge. Now carbon-carbon bond is free to rotate. Thus, it is possible for all CH bond to have eclipsed conformation relative to empty p orbital. In this very situation, the carbon breaking positive charge have tendency to draw electrons from the adjacent and eclipse CH sigma bond, rather than the CH bond under the very atom, because the angle of separation here is 90 degree. Now, this is the sigma bond, where sp3 orbital is involved. It interacts with empty p orbital to form a carbon-carbon pi bond. The 2CH bond becomes planar and becomes sp2 hybridized. The positive charge is taken by hydrogen atom, which is now nothing but a proton and has no bonding. Therefore, hyperconjugation is also called no bond resonance. Hyperconjugation. It is delocalization of sigma electron, also known as sigma pi minus conjugation or no bond resonance. Occurrence: alkene, alkynes, free radicals, carbonium ions. Condition: presence of alpha hydrogen with respect to double bond, triple bond, carbon containing positive charge, that is in carbonium ion, or unpaired electrons, that is in free radicals. You can see here hyperconjugative effect in butene. Hyperconjugation is permanent effect. Effects of hyperconjugation. The first one is bond length. Like resonance, hyperconjugation also affects bond lengths because during the process, the single bond in compound acquires some double bond character and vice versa. Example, C single bond C length in propene is 1.488 angstrom as compared to 1.334 angstrom in ethylene. The second one is dipole moment. Since hyperconjugation causes these development of charges, it also affects the dipole moment of the molecule. The third one is stability of carbonium ions. The order of stability of carbonium ions is as follows: tertiary greater than secondary greater than primary. Above order of stability can be explained by hyperconjugation. In general, greater the number of hydrogen atoms attached to alpha carbon atoms, the more hyperconjugative forms can be written, and thus greater will be stability of carbonium ions. From the given examples, we can observe that tertiary carbonium ion has 9 alpha hydrogen atoms, so 9 hyperconjugative structures, and similarly secondary and primary carbonium ion has 6 and 3 hyperconjugative structures respectively. The fourth one is stability of free radicals. Stability of free radicals can also be explained as that of carbonium ion. The fifth one is orientation influence of methyl group. The O-P directing influence of the methyl group in methyl benzenes is attributed partially to inductive and partly of hyperconjugation effect. You can see here orientation influence of the methyl group due to plus I effect. And you can also see the orientation influence of methyl group due to hyperconjugation.